Hello everyone, this is Dr. Zach again. So for question A, you are going to solve an improper integral. You're going to do the same for question B. Take your time, do a nice job. Did you find that question A was divergent, so that improper integral does not have an answer? And question B is convergent. It has the answer of pi over 6. For today's lesson, we're going to study convergence using an integral test and also the P-series. So for questions A and B, did you use your limit notation correctly? And did you find that question A was divergent, whereas the improper integral for B, the answer went to pi over 6? These problems become important because we're going to study convergence using the integral test and P-series today. The next convergence test that we're going to study is the integral test. And it's a test used in very specific situations. If we have a function f that is positive, continuous, and decreasing, for x is greater than 1, a sub n is equal to a function of n, then we know that the infinite series and the infinite integral must both converge or both diverge. So how this will help us? If we can describe what's happening with our integral, then we will know whether or not our series will converge or diverge. So let's think about how this is going to work. Begin by partitioning your interval from 1 to n. The total area of our inscribed rectangles and the circumscribed rectangles can be given through these sequences. For I equals 2 to n, each one of the rectangular areas can be added up to give you a particular area. Similar things are happening with our circumscribed rectangles. Now, the exact area under the graph of f from x equals 1 all the way to x equals n is going to lie somewhere between these two answers. So if we were to think about that for just a minute, we know that the sum I equals 2 to n f of I has to be less than or equal to the integral, which is your exact area, 1 to n, some function of x dx, where each one of the terms falls on that function, and that has to be less than or equal to I equals 1 to n minus 1 f sub I. We know that the sum, the nth sum, minus the original value at the function, because we don't have I as 1, has to be less than or equal to the integral from 1 to n f of x dx. And that, of course, is going to be less than or equal to our s of n minus 1. Now, if your integral from 1 to n f of x dx converges then to, let's say, L, then for n greater than or equal to 1, we will know that s of n minus the function at 1 is going to be less than or equal to L, and therefore we know that s of n is going to be less than or equal to L plus 1, which makes this bounded. And since it's bounded and monotonic, because our graph is always decreasing in this situation, from a prior theorem, we know that s of n is going to be convergent. So if your integral from 1 to n of f of x dx is convergent, s of n is also convergent. Now, if we have the integral f of x from 1 to n dx is divergent, since it's less than s of n, less than or equal to s of n minus 1, then we also know that s of n minus 1, as well as s of n, is divergent. Which then again leads us to, if our function f is positive, continuous, and decreasing for x is greater than or equal to 1, given a sub n is equal to f of n, then we can say that if our infinite series converges, then our integral converges. Or if our integral converges, then the infinite series converges. Both converge or both diverge. Now, in order to use this theorem, we must first determine if our function is positive, continuous, decreasing, and then we will be able to determine if we have a convergent or divergent function. So, we know that 1 over the square root of k squared plus 25 is always greater than 0. It's continuous everywhere. We're specifically interested for k equals 1 to infinity, but this one is continuous everywhere. And is it decreasing? Yes. Why, yes it is. And you can find the derivative, or you could use a ratio to show that it is decreasing. All right, so we want to determine now. Well, let's think about what the integral did. If we had the integral from 1 to infinity of 1 over square root x squared plus 25 dx. Well, look at that. That looks quite familiar. You did that one earlier. You found out that this was infinity and was divergent. So since this integral was divergent, our infinite series is also divergent. Our second question, let's see if we can apply the integral test. Is our function positive? Yes, it is. Notice that k is always positive from 2 to infinity. So yes. Is our function continuous? You know what? No, it is not. It is discontinuous at k equals 0, at k equals 1, and k equals -1. But that's okay because we're only interested in k's greater than or equal to 2. So is it continuous? Yes. For k's greater than or equal to 2. Is this function decreasing? Yes, it is, and you could use a ratio to prove it. All right, so now, wait a minute. We already found that the integral from 2 to infinity of 1 over x square root x squared minus 1 dx was equal to pi over 6, and because it's equal to pi over 6, our integral was convergent, which tells us that our infinite series is also convergent. So one more time, as you use your integral test, you have to show that your infinite series is positive, continuous, and decreasing. Once you've done that, you could apply the integral test to determine whether your series is convergent or divergent. Next, we're going to look at a very special series called the P-series. We talked about these in an earlier lesson. We are interested to find out if the series n equals 1 to infinity of 1 over n to the p converges or diverges. And that is going to all depend on the value of p. So, from our prior studies, we knew that the integral from 1 to infinity of 1 over x dx diverges. And notice for that, that is when your p is equal to 1. This again had a special name, and it was called your harmonic series. And we also then looked at the integral from 1 to infinity, 1 over x to the p. For values between 0 and 1, we found that this integral was divergent. However, for p's greater than 1, we knew that our integral was convergent. Now, using your integral test, that tells you a lot about what happens to our series. And what does that tell us? It tells us for our infinite series, if p is equal to 1, we have a divergent series. And of course, again, it's a special one. It is harmonic. For p's less than or equal to 1, but bigger than 0, we will have a divergent series. And of course, for the last one, if p is greater than 1, then we know that we have a convergent series. So if we look at example 1, notice that the p-value in this problem is going to be equal to 3 over 2. 3 over 2 is greater than 1. So does this converge or diverge? Since the p is greater than 1, it is a convergent series. There are other tests that you could use, but we need to start recognizing whether they're converging or diverging with less work. Notice that this p-value is less than 1, and that tells us that we have a divergent series. Now, do you remember that nth term test? If we take the limit as n goes to infinity, 1 over n to the 1/3, notice that is equal to 0. This test, remember, told you that it could converge. Could converge, but it did not. This one was divergent. If we use the same test on example 3 and take the limit as n goes to infinity, 1 over n to the 3/2, that was also 0. Again, this test tells us that it could converge, and fortunately, in this problem, the series did converge. Go ahead, practice a few of these problems, and have a great day.